Welcome. Thank you for joining us today. So today is a celebration of the power of science, the joy of curiosity, and the many ways in which science benefits our society. The event is made possible by student volunteers, individual donors, UCLA's Dean and the Division of Physical Sciences, and other academic departments. I'd particularly like to thank one of our major sponsors, alumnus Mani Baumick. Particularly now, it's important for us to come together and celebrate science and the pursuit of knowledge. Science is essential to helping us navigate the pandemic. We've seen a denial of science grow more prominent in this country, and we must reiterate the value of rigorous, fact-based inquiry. Part of this annual event includes the presentation of the Science and Education Pioneer Award from the UCLA Division of Physical Sciences. It recognizes individuals who have demonstrated a commitment to empowering the public to pursue education and success in the sciences. This year's impressive honoree is a superstar at UCLA and far beyond, Andrea Ghez. She is the Lauren B. Leichtman and Arthur E. Levine Chair in Astrophysics and founder and director of the UCLA Galactic Center Group. And I think you all know her by now, that you've heard about her, that she's this year's Nobel Prize winner in physics. The Pioneer Award is incredibly fitting for Professor Ghez. She was recognized by the Nobel Committee for her groundbreaking discovery of the supermassive black hole at the center of the Milky Way galaxy. She's the first woman on the faculty to win a Nobel Prize and the fourth woman ever to win the Nobel Prize in physics. I guess I've thought for many years that Professor Ghez would win a Nobel Prize. I was able to be part of her celebration in Lund, Sweden in 2012 when she received the prestigious Crayford Prize. Nonetheless, I was ecstatic when I saw the text message early in the morning of the Nobel announcements. This recognition is so well deserved. Professor Gez's work is emblematic of our mission and that of our faculty, researchers, and students to pursue scholarship that increases our understanding of the world and our place in it. She's an inspiration to young people the world over who want to pursue careers in STEM fields. She's a wonderful ambassador for UCLA. And I'm so very pleased that she's joining us today to be recognized. So thank you again all for being here. Your support for and interest in the sciences and inspiration to all of us at UCLA. We very much appreciate your enthusiasm, participation, and support. Now, to present the Science and Education Pioneer Award to Professor Ghez, please welcome Dean of the School of Physical Sciences, Miguel García-Garibay.
I started by saying I wanted to thank Chancellor Block first and foremost for joining us today. And I also want to remind you, so my name is Miguel García-Garibay. I am the Dean of the Division of Physical Sciences. And I was making the point that I'm also chemistry and biochemistry, and I'm also welcoming you today to Exploring Our Universe. Exploring Your Universe at UCLA has grown into the largest public science outreach event on our campus, educating and engaging tens of thousands of visitors of all ages. Although Exploring Your Universe is online this year, it is traditionally held at UCLA on the campus. And as such, we acknowledge our presence on the traditional, ancestral, and unceded territory of the Gabrielino Tonka peoples. During your time with us today, I hope you will first and foremost be curious. Scientific discovery is only possible when we keep asking questions like, what if? We encourage you to talk to our friendly UCLA students and scientists and to learn what it's like to be an explorer. Now, it is very important for us to keep this event free and open to the public, open to everyone. And I would like to thank our co-sponsors for making it possible. I'd like to thank Mani Baumick and the Mani L. Baumick Institute for Theoretical Physics. I'd like to thank the Department of Physics and Astronomy, the Department of Earth, Planetary, and Space Sciences, the UCLA Galactic Center Group, and the UCLA Department of Chemistry and Biochemistry. Most of all, I would like to thank our dedicated students on the EYU organizing committee. They have volunteered countless hours to organize today's event. They are Abhijit Simon. She is a structural geologist. Meet Mooney, who makes discoveries on energy storage. Heather Kirkpatrick, who's an expert on geochemistry of the early Earth. Ashna Agarwal, who helps us understand geophysics, fluid dynamics. Ashley Schoenfeld, who explores icy satellites. Krista Sochak, who studies mineralogy. And then we have Grace Wang and Daniel Butts, who are experts in energy storage. And finally, Andrew Parisi, who is an explorer of lunar geochrony. It is also important for us to thank every one of you who makes science possible. Through your contributions to our society, we are able to make discoveries that make life better every day. In fact, federal agencies such as the National Science Foundation, the National Institute of Health, NASA, and others only exist because of the American people's support. So we thank you for that. And now, it is my pleasure to welcome and thank our special guest, Andrea Ghez. Andrea has been a professor at UCLA in the Department of Physics and Astronomy since 1994. Throughout her career, Andrea has been a very strong role model. She inspires students of all ages by taking her science out into the community and participating year after year in events like this. She even published a book for young girls called You Can Be a Woman Astronomer. We're also thrilled that she won the 2020 Nobel Prize in Physics. But it is also important to us that everyone appreciates Andrea's passion as a teacher and a mentor. She is also a gifted communicator who can awaken strong curiosity and enthusiasm in all ages, from grade school children to non-expert grown-ups. Andrea's vision and leadership will not only shape the next era of space science, it will also help us make sure that higher education and research are accessible to anyone who has the desire to pursue it, especially women and students from underrepresented groups. Andrea is a passionate educator as well as an extraordinary researcher. This combination is what makes her such an asset, not only to UCLA and to science, but to our society. It is for these reasons and so many more that we have chosen to recognize Andrea today. Andrea, it is my honor to present you with the 2020 Science Education Pioneer Award. Congratulations, Andrea. We're delighted.
Thank you. And if we were in person, this appeared in my drawer. The frame certificate, and this beautiful crystal. So thank you.
I'm sure everybody is extremely excited to learn a little bit about the discoveries that you made that have been recognized, your live work with the Nobel Prize in Physics. So please, this would be the time to,
thank you.
For all of us to hear from you. Thank you so much, Andrea.
Thank you. Thank you, Chancellor, and thank you, Dean, and thank you all the students who have made today's festival possible. So today we're going to do this in a slightly different fashion. Hopefully this will all work smoothly. Let's see. So hopefully you can see my screen. So today I'd like to share with you a bit about the work that has been recognized by this year's Nobel Prize. This is work that I first started when I joined the faculty at UCLA back in 1994. So conceptually, we started it in 94, and we really got going in 95. So this year, we're actually celebrating our 25th anniversary of the work. And the original science question that we were interested in is the question, is there a supermassive black hole at the center of our galaxy? And really underlying this question is the question, can we prove that these exotic objects really do exist in the universe? And over the last 25 years, what we've been able to do is prove a resoundingly that the answer is yes. These exotic objects that we don't have the physics to describe really do exist, and that we have one at the center of our own galaxy, which provides us with a wonderful laboratory for understanding the physics of black holes, and then the astrophysical role that these black holes play in the formation and evolution of galaxies, which are really the building blocks of our universe. Okay, so let's start off with a question then, which is, how do you observe something you can't see? And this is a really important question for people who study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. So we can't see them directly. But we can actually detect their influence on things around them. So before we get going and understand exactly what I mean by supermassive, let's agree on what a black hole is. So as I said, it's the pull of it's an object whose pull of gravity is so intense that nothing can escape it. But it's doing this because it's an object where gravity has overwhelmed all other known forces and forced an object to become infinitesimally small. In other words, no matter what its mass is, it has zero volume. So if we think about density, which is just mass divided by volume, we're dividing by zero, which means the quantity goes to infinity. And in physics, anytime a number goes to infinity, we call this a singularity, which is equivalent to a giant red arrow that says you don't have your description of physics quite right here, which really means that we don't know how to make the world or the physics that describes things with lots of gravity, which is the world of Einstein, so Einstein's general theory of relativity, work together with the laws of things that are very small, which are the laws of quantum mechanics. So we assume that once we understand how to make these two things work together, we'll understand what a black hole is. And in fact, that's part of the fascination with black holes, is it's the path towards understanding how to reconcile these two fields. Okay, so while these objects have no finite size, there is a size that we can associate it with it, which is known as the Schwarzschild radius. It's also known as the event horizon. So it's the last point, the Schwarzschild radius of the event horizon is the last point that light can escape from the object. So in fact, we can't get any information from inside the Schwarzschild radius. But it's also important because it's at that radius that gravity overwhelms all other known forces. So every object has a Schwarzschild radius associated with it, and it simply scales with the mass of the object. So if we were to look at the Earth, and if there were some way to squeeze the Earth down to the scale of a sugar cube, it would be forced to become the infinitesimally small object known as the black hole. Now, the radius scales linearly, so directly proportionally to the mass. So if we were to take the sun and scale it down to, and I couldn't resist, UCLA's campus, go Bruins, it would become a black hole. Now, in astrophysics, we think about and talk about two classes of black holes, and they really nicely represent the two ways in which science emerges. The first way, the first type that I want to mention are what I'm going to call stellar mass black holes. And these black holes were the first to be recognized. And in fact, it was from theoretical work. So people thinking about what might happen or describing the physics from a theoretical perspective, thinking about what happens with very massive stars when they end their lives. So stars that are more than 30 times the mass of the sun will end their lives doing two things that are quite spectacular. So the outer layers of these massive stars explode. So we get a supernova explosion, and the outer layers are jettisoned off. And so that's what you're seeing in this spectacular picture, is the outer layers flying off into interstellar space. But in the middle, the core of the object will actually collapse under its own gravity and become a black hole. So these stellar mass black holes are thought to be roughly 10 times the mass of the sun. They were predicted. In fact, it was the prediction that gave the nickname of these objects, black holes, recognizing that they wouldn't emit light. And now we found observational evidence for them. So the observations came second. The kind of black holes that I'm particularly interested in are in the second category. They're known as the supermassive black holes because they're much more massive. So rather than being 10 times the mass of the sun, they're 1 million to 1 billion times the mass of the sun. And we think that they reside at the center of a galaxy. So in this picture, we're looking at a vastly different scale here. Every object in this picture, except one object and one or two objects that have the crosses on them. Those are stars in our own galaxy, but the rest of them are galaxies outside our own. And if we zoom into this spiral galaxy, which you can see on the top left, this is a spiral galaxy that has roughly 100 billion stars. So in the last image, we were looking at a single star, and here we're looking at many, many more stars. So the scale is quite different. And there's nothing in this picture that made people think that there were supermassive black holes, but rather, what happened is that observations of galaxies at radio wavelengths, these are taken at optical wavelengths, which is what your eye detects. So if we go out to the radio, which is where your cell phone works, some of these galaxies exhibit really unusual phenomena. So this is a single galaxy. The starlight, you don't see the stars so well in the radio, but what you do see emanating out from the center are these jets, and these jets are moving incredibly fast. So you can infer that there's a lot of energy. So something very powerful has to be driving this energetic energy. Furthermore, at the center, there's light that has characteristics unlike anything emitted by stars or gas. So it's assumed what people started to think, driven by the observations. So you can see how the story here is different. The observations lead. This led people to think that this was matter falling onto the black hole. In other words, through that short chill radius and event horizon, you're seeing light that gets very hot right outside that point. So you can think of these black holes as being lit up because they're accreting a lot of matter. Or another way of thinking about it, you could say that you're looking at the dining habits of these black holes. These only happen in very energetic galaxies known as active galactic nuclei, simply because their nuclei or centers are very active. So these are 10% of all galaxies. So in a way, you can think of these as being the prima donnas of the galaxy world. But they are what led people to speculate on the possibility that supermassive black holes could be at their centers and driving all the energy that we're detecting. About 50 years ago, that led people to speculate that could it be possible that supermassive black holes reside in all galaxies, not just these energetic show-offs. So this is a zoom in to that spiral galaxy that we were looking at in the frame before in the optical. And this is what our galaxy would look like if we could get outside it and look back. And our galaxy is certainly the best place to look for the center for a black hole, because it's the closest center of a galaxy that we'll ever have to study. Now, we have an interesting perspective on our own galaxy, because in fact, if you think of the center of the galaxy as sort of the crowded downtown urban center, we're kind of out halfway out in the suburbs, and we're looking back into the center. Because galaxies, for the most part, are flattened disk-like structures, when we look into the center, what we see is this line of light. So if you go to a dark site, certainly not from Los Angeles, and look up during the summer in particular, you see this band of light known as, and that's the plane of the Milky Way. What you might notice is not only do you see that plane of light, which represents which is all the stars in our own galaxy, which are from the light from the stars in our own galaxy, you might notice that there's a dark band in the middle of the galaxy as well. And that's because our galaxy has not only stars and gas, but a lot of dust. Now, if you're in Los Angeles, we have a very good appreciation for what dust in the air does. This is like dust that causes smog. It's very good at blocking optical light that your eye detects. So in fact, only 1 out of 10 billion photons, light packets, makes it to us from the center of the galaxy at optical wavelengths. But if you look in the infrared light, which is where your TV remote control works, that kind of light can get through all this dust, can penetrate the dust. So 1 out of every 10 photons makes it to us. So in fact, all the work that I'll be describing or that we've worked on for the last 25 years has been done using infrared technology. And this is something that UCLA is extremely good at. We've invested a tremendous amount in the technology and science of infrared astronomy and astrophysics. Now, the goal here is to prove that there's a supermassive black hole at the center of our own galaxy. And if the best way or the most direct way to do that is to look at the influence of that black hole on the things around it. So the stars at the center of the galaxy are going to orbit whatever is inside its their orbits, very much like why the planets orbit the sun. It's the gravity of the sun that make the planets go around. And these stars are actually orbiting the black hole for the exact same reason. It's the gravitation of the black hole and whatever else is inside the orbit of the star. So what we want to show is that there's a lot of mass confined within its Schwarzschild radius. So the orbits of these stars very directly give us the mass, and then the scale of the orbit tells you the scale to which you've confined the mass. So you want to find the stars that are as close to the heart of the galaxy as possible, because those are the stars that really tell you the answer about whether or not there's a supermassive black hole at the center of the galaxy, or ultimately provide the demonstration that these exotic objects exist. So to see the stars that are as close to the center of the galaxy, that goal tells you why I actually wanted my job at UCLA. I think I have my dream job without a doubt, because at UCLA, I have access to the world's largest telescope. So that's the Keck Telescope. The Keck Telescopes are co-owned by the University of California and Caltech, and UCLA has built all the infrared instruments, which is basically half the instrumentation at Keck Observatory. These telescopes telescopes in general are described by the diameter of the primary mirror, the mirror that collects the light. And Keck is a 10-meter class telescope. So that means the width of the primary mirror is 10 meters. And to give you a sense of scale, that's like the width of a tennis court. And we're fortunate enough that there's actually 2 telescopes at this scale. And these telescopes are up on the top of Mauna Kea. And we can talk about, Mauna Kea is just simply one of the best places on this planet to build telescopes. So there are about a dozen telescopes from all around the world at this site. Now, the campaign promise of large telescopes are twofold. One is that by building a larger telescope, you should be able to see light from much fainter stars. So you can think of a telescope as a big light bucket. So that's promise number 1. And promise number 2 is that the larger the telescope, the finer the detail that you should be able to see. So this means that you have fine angular resolution. And the way I like to describe this is if you think about a painting made with the technique of pointillism, but with the dots, as you get closer to that painting, your ability to resolve the detail, your resolving power increases. So in astronomy, the way to increase your resolving power is by increasing your telescope diameter. So the larger the telescope, the finer the detail you should be able to see. So the first campaign promise has been easily achieved for hundreds of years. But the second has been much harder to achieve, and that's because of the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive here on Earth, but it is a total headache for people studying the universe. So what we're looking at here are 5 bright stars that are at the center of the galaxy. And the light, if there were no atmosphere, would be the scale of the smallest structures that you're seeing dance around, and they would be rock solid still. So, and that's because of the turbulence in the Earth's atmosphere. It just distorts the astronomical images. And it's actually rather profound if you think about it. The light from the center of the galaxy has been traveling to us for 26,000 years. And in the last 30 microseconds, hits the top of the atmosphere and gets completely messed up. So I've spent a lot of my career thinking about and developing techniques for overcoming the distorting effects of the Earth's atmosphere. And in fact, there's been a huge change in the technology that we've used over the course of the 25 years. So this is a project that for which time helps you. The longer you make the measurements, the better they become. But also, the better your technology, the better these measurements become. So technology has been a key factor here for us. And this animation shows you a little bit. You actually can see the 5 bright stars that we were looking at the bug splat pattern. And if you take a long exposure, the first animation had an exposure time of 1/10 of a second. And that's too short to really do science. So you have to take longer exposures. And if you just take them and add them up, which is typically what you would do, you get the big blur. And by using these techniques, we can overcome the blurring effects and get to the diffraction limit, the ultimate resolution of the telescope. We think the black hole is inside the little square that's in the center of the image here. So while we track thousands of stars, the ones that are going to tell us whether or not there's a black hole are in the middle of this inset box. And you can see without being able to take these higher resolution images, it's a big blurry mess. There's a lot that could be said, and I encourage you to come by our booth later on to learn more about these technologies. But let me just briefly say that while we started with relatively simple techniques, the ultimate goal was to introduce mirrors that actually correct for the atmosphere in real time. And this is a technique that was actually developed in the military. The military cares about looking up and down, so through the atmosphere. So it's a wonderful example of declassified information having tremendous impact in the sciences. Now, this happened because the astrophysics community was starting to figure out how to do this. There's far less money in this field, but we were certainly figuring it out. So in the early 90s, it got declassified, and then the game became, or the goal became, to just figure out how to correct or to use this in an astronomical setting. I just wanted to say a few words about this because we show this image a lot, and the reason these lasers are important is not is because what we do is we create an artificial star up in a very thin layer of sodium atoms that get trapped. So meteorites, so if you ever go and wish upon a shooting star, you're actually wishing upon a meteorite that's breaking up in the atmosphere and providing a very important source of sodium atoms that we can stimulate to shine like a star. So we create an artificial star that allows us to figure out that distorting effect of the Earth's atmosphere. Okay, so let's look at how those stars have moved over the last 25 years. We're going to look at a box now that's 1/4 the scale of that inset box. And it's gotten more interesting than we could possibly imagine. And I say that because, in fact, when we first proposed this project, it was turned down. It was turned down because people didn't think the technology would work. And even if we did, we wouldn't see the stars. And even if we could see stars, we wouldn't see them move. So I love looking at this movie. You can probably figure out what my favorite star is. Its name is SO2. Probably needs a better name, but it basically has a number that helps us understand where it is. There's a lot encoded in this animation. Stars are discovered in an image. So you take a picture and you see the stars. They're trailed by a dashed line. And you may see stars just pop up, and that's because the imaging capability becomes better. It's not that the stars become brighter. It's just our ability to see things that are fainter improves. And then once we can take spectra, and spectra allows us to see the third dimension of motion. So images, you take a sequence of images and you can see how things move on the plane of the sky, and that's what we're seeing here. And then the spectra allows us to see how things move along the line of sight. Okay, so what has this done for us? What has SO2 done for us? So it goes around every 16 years. And this is just amazing that it goes around on a human lifetime. The sun takes 200 million years to go around the center of the galaxy. And these stars are taking on order of a decade. And the fact that they're going around so much provides us with the ultimate piece of information that we need. So at the beginning of this experiment, we had 4 million times the mass of the sun inside a region that's the size of the circle. And this experiment has shown us that, in fact, this 4 million times the mass of the sun is confined to a volume that's a factor of 10 million times smaller. We can actually show that there's 4 million times the mass of the sun within a scale that corresponds to the size of our solar system. And if you think about that, our solar system has one sun, and this region of space has 4 million times more mass confined to that same region. And now we're approaching, in fact, the Schwarzschild radius of a 4 million solar mass black hole. And in fact, this has provided us with the strongest evidence to date for the existence of a supermassive black hole, not only in our own galaxy, but in fact, anywhere in our universe. So we've increased the evidence for a supermassive black hole by a factor of 10 million, bringing the notion of a black hole, these supermassive black holes, from a possibility to a certainty. And now this is ultimately what's being recognized with this year's Nobel Prize. The observational side, there are two recipients, myself and a group in Germany. These two groups have been at it for 25 years, and there's tremendous benefit to competition. It keeps you on your toes. It provides independence of thought. And these measurements, while you can describe them in a simple way, are actually quite subtle. There's a lot of ways to get them wrong. So it's tremendously beneficial. We've learned a lot from each other over the last 25 years. Now, I just want to end with saying there's so much more that can be done. So we've actually done this work with one clear question that we have a very clear answer for. But in fact, the technology gives us such a new view on the center of the galaxy that we're actually unveiling more questions than answers. And that's often, where research just gets to be tremendously fun. And we're actually now thinking about questions that we can answer that we couldn't possibly have dreamt about at the beginning of this work. So it's been an amazing journey. So just to give you a sense maybe of some of the issues. When we first proposed this work, people asked which came first, the galaxy or the black hole. It was somewhat like the chicken or the egg question. And what we understand today, and at that time, there were explanations for both. I mean, we had ideas for why the black hole might form first and the galaxy would form around it, or how the galaxy formed first and the black hole formed out of it. But what has become apparent sort of halfway through this work, as other candidate supermassive black holes were being found in other galaxies, the mass of the black hole in these other galaxies seemed to always correlate with the mass of the central part of the galaxy, known as the bulge. And this, the scale of these objects are so vastly different that whatever caused the black hole to form had to be synergistic with the formation of our galaxy. So in other words, they form together. There's not which came first. The same thing had to form both objects. And that over time, as the black hole grows and as the galaxy grows, there's some sort of feedback that has to be at work between the black hole in the galaxy. In other words, we've come to understand that these supermassive black holes have a very important regulatory role in galaxies. And our own galaxy offers us an amazing place to understand this process. There's a number of predictions that can be made. And again, looking at our own galaxy, one of the things that I have to say, this is supposed to be playing. Let me just go back and see if I can get it to play. If we're patient, it may decide to play. I think it's huge. This is an animation if it decides to animate. If it doesn't, you'll see that there are many stars that have orbits. This was designed to pull back, to give you a sense of scale. Oh, it's gonna go. And there are a number of predictions that you can make about what kinds of stars that you can see at the center of the galaxy. And all these predictions are inconsistent with the observations. So one prediction is that there should be no young stars at the center of the galaxy because star formation requires that very fragile balls of gas and dust. So these really fragile nurseries collapse. And if you put something near a black hole, one side is pulled more strongly than the other. So in other words, if you were to fall feet in first into the black hole, your feet would be pulled more strongly than your head and you would be torn apart, what we like to call spaghettified. So these young stars shouldn't form. Those are the aqua green things. So in fact, they're the most common things that we see at the center of the galaxy. The other prediction is that there should be lots of old stars because these old stars have had plenty of time to interact with their surrounding. And yet those are the orange stars and there are very few of them. And then the pink stars that you see in the center here are things that we didn't think to predict. So these are causing us to scratch our heads even more strongly or deeply than the young star or the old star. So that's just a sense of flavor. All right, for some reason, this is not playing on this platform. Another aspect of the work, which has to do with understanding the physics of black holes or the physics associated with black holes, is to try to understand how gravity works near a supermassive black hole. As I said in the beginning, black holes themselves represent the breakdown of our description of the laws of physics, the laws of gravity with the laws of quantum mechanics. And so what we want to do is get as close to the black hole as possible to see how well the laws of gravity are working. In other words, at some point as you approach this object where things break down, you should see the imprint of whatever the bigger picture of how gravity works, the underlying, more complete version. This is a classic picture that's often depicted at science museums. It collapses the 3 dimensions of space into 2 and uses the third as time. So as you get near a black hole, there's a mixing of space and time. And what's so fun about these objects that we've discovered at the center of the galaxy is that they're orbiting, and they're orbiting such that their position in terms of how much space and time is being mixed changes over the course of their orbits. So today we're deep into making tests of Einstein's general theory of relativity, both in terms of how light escapes out of the gravitational potential. In other words, how that warping of space-time affects light, and how the object itself is going around. And in fact, today there's even more surprises that are emerging on that front. So that's just to give you a sense that we are still hard at work. We're having a tremendous amount of fun in terms of understanding the things that we both set out to discover and the things that we did not intend to, but because technology has given us a new view, we're understanding that we need to go back to the drawing board with some of our ideas. We're also pushing or advancing more on the technology. Today, as you saw in those other images, we only use one laser to correct for the distorting effects of the Earth's atmosphere. Today, we're working on much more advanced systems that allow us to more completely get sharp images. And that's essential as you go to a larger and larger telescope, because you miss some of the light by just using one. And the fraction that you miss gets bigger and bigger as you go to larger and larger telescopes. Today, we're also working on the next generation of telescopes, what comes next after Keck, and for the University of California, that's the 30-meter telescope. This is an incredibly exciting project. As the name suggests, it's 30 meters across. This is like a baseball diamond now. This will be the largest moving structure ever built on the Earth, and will give us unprecedented views of the universe. This animation just gives you a sense, moving from the left, where we are today, to the middle, this new technology on today's telescope, and then what this new technology, which is necessary to get to the diffraction limit or the ultimate resolution of the 30-meter telescope. And today we really just see the tip of the iceberg of what's actually at the center of the galaxy. So we're very excited to see what the overall population looks like. And presumably these will give us important clues to understanding the unexpected things that we see today. I just want to give a shout out to my long-term collaborators, Mark Morris and Eric Becklin, who are other faculty at UCLA who I've had the true pleasure of collaborating with for the last 25 years. This project started with a very small collaboration on the right, and Ms. Beth Klein, my very first grad student. Today, the collaboration is much larger. We have a core collaboration of about 30 people. Here we are up on the top of Mauna Kea, and a broader collaboration network that expands to about 100 people, because there's such a diversity of science that can be done with this 25-year data set. In case you're wondering, what do students do after they graduate in a field like this? Well, students go on to do all sorts of things. Students go on to, some of them become professors in astronomy and astrophysics, but others go off and work for the military. They go off and work for the financial industry, and increasingly, many of the students are going off to work in big data fields. So our data sets are quite large and quite complex. So the students working in these groups have wonderful training to go into a diversity of fields. And last but not least, I want to acknowledge the support that we've had from a large number of folks over the last 25 years. All of this requires support to do the research that we do. So UCLA, the Heising-Simons Foundation, the Sloan Foundation, the Keck Foundation, the Packard Foundation, the MacArthur Foundation, the Moore Foundation, and then the wonderful members of our Star Society group. So I'm really grateful for the support that people at different points over the last 25 years have provided. Oh, and I shouldn't forget, right in the middle, and has been really the backbone of this work, is the National Science Foundation. Okay, so with that, if nothing else, I hope I've convinced you that there's a supermassive black hole at the center of our galaxy, and that we have now uncovered more questions and answers. And to learn more, I encourage you to come visit us today at the Galactic Center booth. Okay, so thank you for your attention.
Thank you, Dr. Ghez. This was really, really exciting. I'm sorry you can't see my face at the moment. You know, when I was in high school, we were talking about the supermassive black hole as just sort of an idea. And, you know, maybe someday there'll be actual proof of it. And now here it is. So this is really, really great. We had a couple of quick questions in from the audience. So somebody wanted to know, do black holes die, or can they just absorb and grow forever? Or can they do both?
Oh, that's a great question. So the ultimate evolution of the universe is actually these big black holes. These black holes, they keep growing. Very small black holes can evaporate, but it's only on the very smallest scales that are much smaller than even the stellar mass black holes. So black holes kind of are the final state of the universe.
And one more. So what happens if two black holes were to collide with each other? Would they just eat each other? Would they go bouncing off to the end of the universe? What happens there?
So in fact, galaxies collide with one another. That's a very common occurrence between galaxies over long time scales. So we're actually headed towards Andromeda. Nothing for us to worry about on our time scales, but ultimately the Milky Way and Andromeda will collide. And both galaxies have supermassive black holes. And so what will happen is that the two galaxies will become one. And the most massive things will sink to the middle. So the two supermassive black holes will sink to the middle, and they'll spiral in, and they'll merge to become yet bigger supermassive black holes. But when they merge, there will be a blast of gravitational radiation that's sent through the universe. And in fact, that kind of radiation is what a future mission called LISA, space mission, which is a gravitational wave detector in space. It's kind of like putting LIGO in space.
Thank you so very, very much for being here. Like I said, that was a great talk. I'm sure everyone is giving you a virtual round of applause, and we can imagine what the clapping would sound like. Yeah, no, thank you again from all of us.
You're welcome. Thank you.
Thank you, Andrew. Andrew Parisi is one of the organizers of EYU, and we're very grateful for all the work that he and his colleagues have done for it. And your talk's absolutely fascinating. And so I just want to congratulate you and thanking you for helping us understand our universe much, much better than we had before. It's fantastic. And so I will leave, but not before I introduce the president of the student organization, and that is Abijah Simon. And for Abijah to join us in, I will leave and invite you to please join us in the booths, check out the talks, go to the question and answer sessions. Abijah, I'm leaving, and the floor will be all yours. Thank you, everybody.
Thank you to our Chancellor and the Dean for the fantastic introduction, and especially to Andrea for that amazing talk about black holes. I definitely learned a lot, and I hope you all did too. My name is Abijah Simon, and I am a PhD student at UCLA and the president of Exploring Your Universe. I wanted to take a minute to thank the rest of my team of UCLA graduate students who have volunteered countless hours behind the scenes to organize this event. I think they'll come. Our organizing committee consists of Mitt Mooney, our finance chair, Andrew Parisi, our speaker and Q&A chair, Heather Kirkpatrick and Ashna Agarwal, our communication chairs, Ashley Schoenfeld and Krista Sawchuk, our technology chairs, and Grace Wang and Daniel Butts, our outreach chairs. We are so proud to see this event come together and to see all of you here. I would also like to thank the hundreds of volunteers, including our science speakers, booth leaders, booth volunteers, Q&A panelists, event moderators, and other volunteers who are hosting all of the events that you see today. Thank you again to our sponsors that Dean Miguel mentioned in helping us to keep this event free and accessible to everyone. And finally, thank you all for coming to this event, supporting science education, and helping us to share this importance of science with others. We hope that you enjoy all of the activities that we have lined up for you today, and please have a wonderful time at Exploring Your Universe.